All right, in this video, we're going to go over calculating truss forces. I'm going to go over the example problem in this PowerPoint, just as the PowerPoint shows, and then I'm going to do another example problem for you on another video. So make sure that you watch the second one as well so that you feel like you have a better understanding of these truss calculations. Okay, the first thing we need to talk about is compression and tension. Whenever you have a beam or a member on your bridge or your structure, it's going to be considered either under compression or it's under tension. Now, tension is whenever you're pulling it apart, just like in those free body diagrams we were doing earlier, how if it was like a cable or something and it was pulling it away from the joint, then it was tension. So if you want to kind of picture this as like the joint or the gusset plate, and then those forces are pulling away from that. And then compression is whenever you're pushing, there's pressure on that member or that beam, which is then causing pressure to be forced into that gusset plate. And that's what this is representing here. All right, a body is being squeezed. In the case of what we're looking at, they're those beams. All right, so a truss is composed of slender members joined together at either end points. They're usually joined by welds or gussets. Okay, these right here are your gusset plates. Okay, and they're usually welded. And those are done at the joints. All right, a simple truss is composed of triangles, which will retain their shape even when removed from supports. Okay, so if you get the triangular shape, notice it's going to be a little bit stronger, or not a little, a lot stronger with the triangle shapes. It does help. All right, at this point we've already talked about pinned and rollers. All right, so pinned is the actual place where it's being held tight. The roller is the location where it's just being held up. It's kind of that normal force. In the truss calculations, we call it a reaction force, but it's just being held up so that gravity does not pull it down. But it is allowed to expand and contract based on weather or whatever conditions. All right, now whenever we do these truss calculations, we have to make assumptions because we are not at that point in math where we're going to not have these assumptions. Of course, whenever you're actually building a bridge, you're going to have the math required and you'll be able to go ahead and add in the calculus and not have to make these assumptions. But this is a great place to start, a place to start learning some of these calculations. So your assumptions that we're making is all members are perfectly straight. All loads are applied at the joints. All joints are pinned and frictionless. Each member has no weight. Members can only experience tension or compression forces. So as you kind of look through those, you can understand when we say we're making pretty big assumptions here, but this is just in the purposes of being able to do the math at the level that you're at. Which risks might these assumptions pose if we were designing an actual bridge? Obviously, the no weight is the big red flag that I see. Obviously, bridges themselves are very heavy. Okay, so before we do an actual truss calculation, we have to decide, is it worth my time? If it's not ever going to be statically determinate, then there's really no purpose in doing the math. So the way you're going to solve this, and I don't know if you've seen this before or not, but we're going to look at this 2J equals M plus R, where J is the number of joints, M is your number of members, R is your number of reactions. So let's look at one of these here. All right, remember each pin has two reaction forces, one in the X and then one in the Y. So we'll start left to right. 2 times J, J being my joints. I have 1, 2, 3, 4 joints. So 2 times 4 is 8 equals M plus R, my number of members, 1, 2, 3, 4, 5. So this would be 5 plus R. My number of reaction forces here is 2 and 2, so that's 4. So 5 plus 4 being 9. 9 does not equal 8. In this instance, we would not do the problem, or we would be asked to fix it. how can we fix it? Well, we can make one of those a roller. It has to have room for that expansion. So now if you try it, you'll notice we have 2 times 4 is 8 equals 5 plus, now we have 2 here, 1 here, so 3. 5 plus 3 does equal 8. Okay. And you'll notice this on all bridges. Of course, we don't really have time to go and count all of those members and all of the joints, but if you did, you would find that yes, they are statically determinate or they wouldn't have been built. Okay, so just some of the reminders from the beams before. You need to remember that the sum of all the moments have to equal 0. The sum of all the forces in your X have to equal 0. Right, sum of all your forces in your Y also have to equal 0. Okay, and remember your positives and negatives as it's showing here. If it's going up, it's going to be positive. If it's going down, it's going to be negative. On the x's, if it's going left, it's negative. Going right, it's positive. And then moments, of course, we're looking at those in clockwise is negative, counterclockwise is negative. Let me try that again. Counterclockwise is positive. All right, because of your Cartesian coordinate system, if you think about that. Okay, so here is the truss that we're going to be working on. All right, and it's also talking about your moments here. A force that causes a clockwise moment is negative. A force that causes a counterclockwise moment is positive. All right, so if we look at these, we can decide which ones are causing the moments to be positive and which ones are going to be negative. Okay, so as it says here, this force D would cause the pin, it would cause it to go in this direction, which is clockwise. So my moment here, I need to be looking at it as negative. On this one, my CY, whenever it is being forced, if this force would cause it to move, it would cause it to go in this direction, which is counterclockwise. So we're looking at that moment as positive. All right, sum of all my moments equals 0. I know usually I work these where I look at my forces first, but you really don't have to look at your forces first. You can do your moments first. All right, so let's go ahead and look at this. Now, I really liked how Mrs. Krumsick did the example problem on the beams and explained to you that we're looking at all forces. So if I looked at the moment at RAX, because when I'm looking at the sum of all the moments, I'm also needing to figure in my x's and my y forces. So here we would have RAX, but because this is our pin, that distance is 0. So it cancels it out. Then if I am looking at my RAY, this is not labeled correctly, this RAY, then its distance is 0. So I would have a 0 plus a 0 moment in this case. But moving on from the pin, we've got at force D, we've got a 500. Okay, so a negative 500 because of the moment is negative times 3 feet plus, moving on along, RCY times 10 feet, all having to be equal to 0. Okay. So then I calculate it, solving for RCY, and I do find my RCY is 150 pounds. Right, so the next thing that we have to look at is our forces. The sum of all my forces in my Y is equal to 0. So I have to look at all of my Y. I have RAY, I have my force at D, and I have this 150 pounds that I just found out, which is the reaction force at C. This one's going down at D, so I have a negative value. The reaction forces are going up, so that's why those are positive. Okay, filling in all that I know. And then I can solve for RAY because it's my only unknown. Okay, giving me 350 pounds. Okay, so at this point I've found the reaction forces in the Y, and now I need to find the reaction force in the X. Again, sum of all the forces in the X have to equal 0. I happen to have only one X in this case. So because of that, I know that the reaction force at point A in the X direction is 0. Okay, at this point we need to start figuring out what kind of force is on each of my members. Right? Will it be able to withstand that amount of force? Materials react differently if they are under compression or if they're under tension. So I also need to know which one it is. Is it under tension? Is it under compression? And will that material withstand that amount of pressure? Or am I going to need to make it out of something different or redesign it? All right, so use cosine and sine to determine your x and y vector components when we get into each of these joints and finding the members. You need to assume all of the members are in tension. Now, obviously, they're not all in tension, but we have to start somewhere. So we're going to assume they're all in tension. So we're going to assume that they're all going away from the joints. Okay, notice I'm going to draw them all this direction. So then when I get a positive answer, I know it's in the member is in tension. If I get a negative number, then I know that it was actually in compression. Okay, so all forces are solved. Update your free body diagrams as we go. Okay, so let's look at it. I know that my distance is 3 foot, 7 foot, and then the height is 4 foot. I do not have these angles, so I'm going to have to start off by finding those angles. And I would do that by using tangent. Okay, so this first angle is going to be tangent, opposite, which is 4, over adjacent, which is 3. Okay, so 4 divided by 3. Then I'm going to take the inverse tangent of that so that I can find out what the angle is. And it's 53.13 degrees. Okay, do the same thing for the other side so I can get that angle. Okay, opposite over adjacent, 4 divided by 7, inverse tangent, and it gives me 29.745 degrees. If you're not getting these angles, make sure that your calculator is in degrees. Okay, so now I need to break it all down. I need to break it down into each joint as its own vector that I'm solving. Okay, so I'm going to break this down so that I'm going to look at A first. Notice each of these members are now called by the name between the joints. So this is AB, this one here is BC, CD, AD, and then this one here is actually not labeled, but it's BD. Okay. Then you need to fill in. You do not need to be using reaction because we already know what those forces are. Okay, so we're going to start off by looking at A. We're going to solve it the same way. We need the sum of all the forces in the X to equal 0, sum of all the forces in the Y to equal 0. On these, you're going to go ahead and start with the sum of all the forces in your X. In your Y. We're going to start with the Y. All right, sum of all the forces in my Y have to equal 0. I know that all the forces in the Y, I've got RAY, which happens to be 350, positive 350. And then I also have a Y component from this AB. You need to find what those components are. And if you remember, it is your force, so that would be AB, times the sine of the angle is going to give you that, in this case, it's the Y component. In a minute, whenever I find the X components, I'm going to still do AB, which is my force, times the cosine of my angle. And the reason why we're using sine in this case is because I'm trying to find the Y, which would be opposite. Right, so opposite is going to be your sine. So then I can solve for AB. So I go through and I solve for AB, which is negative 438 pounds. Now, because it's a negative, I know it's under compression. So I need to change my angle, or not really the angle, I'm sorry. I need to change my arrow. I need to change my arrow going into the joint instead. Okay, now we're ready to find all the forces in the X. All right, sum of all my forces in my X are 0. I have a negative ABX, because notice it's going down. So it's in the X direction is negative. And that's why they have a negative ABX plus AD. Of course, we also had a reaction force here, but it was 0 as well. Do you remember we had reaction AX, and that equaled 0. And so they just left it off. I usually go ahead and add those just so I can keep them all straight, but on this PowerPoint they didn't. All right, filling it in, I've got negative 437.50 pounds. Okay, that's what I just found that to be, times cosine of my angle is going to give me the x component of this vector right here. Okay, so I'm going to get that value plus AD. AD is an unknown, so we're going to solve for AD. Notice we're using cosine this time because here's my angle. I'm looking for the one that is adjacent. And to me, it looks like it kind of makes a C, and that's how I remember it. Okay, solving for AD. I know that AD is 262.5 pounds. That means it is under tension, and I'm going to leave that angle or that arrow the way it is. Okay, so now I'm going to go over to the other joint that has the reaction on it. Okay, you always want to do those first because that is where you have most of your information. So my force and all my y, but sum of all my forces in my y have to equal 0. All right, so my RCy, which is 150, going up, so it's positive, plus BCy, right, which is this vector right here. I'm going to find the y component of it. Okay, notice this right here. So we're looking at opposite, which is sine. So 150 pounds plus BC is the force, we don't know yet, times sine of 29.745 degrees. Now I'm going to solve for BC. Finding that BC is a negative 302 pounds. Negative tells me it's under compression. Got to change my arrow. Okay, so now we're ready to do the sum of all the forces in the X equaling 0. In X, I've got CD. It's going to the left, so that's why it's negative there. And then I have BC in the X direction. I've got that value. It's going to be in the X direction, so I know that it is cosine. So I'll say the force, which is 302.33 pounds, notice it's a positive because it's going towards the right, times cosine of 29.745 minus CD. I do not know CD yet. I'm solving for it. Punch it in. Notice it is positive again, so it's under tension, and I do not need to change my arrow. Okay, at this point, I've got sum of all my forces in my y, BD, minus FD. Notice this one's going up, so it's positive. This one's going down, so it's negative, meaning that BD is 500 pounds. So if I break them down into each joint, it makes it a little bit easier to look at. And of course it's positive, so it's tension. I don't need to change my arrow. Okay, so at this point, I do not have to do B, and I'm going to go ahead and kind of go back to that real quick so you can see this. If I can get to it. Notice here I found AD, I found CD, I found AB and BC, and even though this one wasn't labeled, we found BD. So that means then if I look at joint B, I don't have any calculations to do for that one because I have found them by using the other 3 joints. Okay, so now watch my next video. I'm going to be doing an example problem, a different one that is not on this PowerPoint, and I'll actually work through it on paper.